Hello everyone. So today's lesson is going to be regarding chapter 9, which is all about chemical bonding. So in this chapter we will talk about the basic concepts regarding bonding between atoms within a given compound. So I want to start off this lesson by asking these questions. How do atoms bond together in order to form molecules? How do chemical bonds form? And how do we know that they are stable? In order to answer these questions, we have to use what they call bonding theories. And there's a variety of them. There's a lot of different types of bonding theories, and they range from basic to quite advanced. Now, these bonding theories are basically models that predict how atoms form bonds within a given compound, like molecular compounds and ionic compounds. They can explain the stability and reactivity of molecules, and they can be used to predict the shapes of molecules. So learning about molecular shapes is very important, especially in understanding different cellular interactions as well as development of medicine. There are many different types of models and theories, some of which can explain certain phenomena better and more accurately. So one example is the Lewis model, and this is actually one of the simplest models in bonding theory. And this is also known as the Lewis theory. So in this model, Lewis structures or Lewis electron dot structures are drawn to illustrate molecules in which the valence electrons are represented by dots. So this model basically shows you the connections or the bonding between the atoms. So for example, if you have a water molecule, so water is H2O. So the two hydrogens in H2O are bonded to the oxygen atom, and this forms a very stable molecular structure. This Lewis model can also be used to predict whether a set of atoms will form a stable molecule and what it looks like. So atoms within a given compound are connected together via what they call chemical bonds. And there are three different types of chemical bonds. There's ionic bond, covalent bond, and metallic bond. But in the next two chapters, our focus will be on the first two, ionic bonding and covalent bonding. So what's the difference between these three different types of chemical bonds? The first one is ionic bond, and this is the bond between a metal and a non-metal in which electrons are being transferred. Okay, so metals, if you remember, tend to lose electrons, whereas non-metals tend to gain electrons. So when the metals lose the electron, that electron is actually transferred to the non-metal. So it's the transfer of electron that's involved in ionic bonding. So you have what they call electrostatic interactions between the metal and the non-metal ions. Covalent bond, on the other hand, is the sharing of electrons. So this is the bond between non-metals only, in which electrons are being shared. But this is not actually exclusively for non-metals. Covalent bonding is also observed in some metals as well. So, for example, if you have a gold atom that's bonded to a sulfur atom or an oxygen atom, the nature of that bonding is actually covalent. And that's kind of a more advanced topic. The third type of bonding is called metallic bonding. So this is the bond between metal atoms, like for example, gold atom, silver atom, sodium atom, and so on and so forth. So this is the bond between metal atoms in which electrons are pulled together and delocalize within the entire metal. So here's a few examples. We have ionic compounds in which ionic bond is being utilized. So we have salts like sodium chloride, magnesium fluoride, and aluminum oxide. So as you can see here, we have electrostatic interactions between the positively charged cations and the negatively charged anions. And electrons are basically being transferred from the metals to the non-metals. And here's a few examples of molecules in which covalent bonding is being utilized. So here we have hydrogen gas, hydrogen fluoride, and NH3, which is basically ammonia. Other molecules like caffeine and sugar, as well as alcohols, also use this type of chemical bond. And the last example here is for metallic bonding. So metallic bond is present in all metals, like sodium metal, gold metal, and magnesium metal. So earlier we mentioned that the Lewis theory is the simplest bonding model. And before you can learn how to draw the Lewis dot structures of any molecules, first you need to understand and learn how to draw Lewis symbols. And Lewis symbols are basically the symbol of the element surrounded by dots. And the dots represent the valence electrons, the number of valence electrons. So just a quick recap here. The number of valence electrons for a given element is determined by the element's group number. So for example, elements in group 1A will have 1 valence electron. Elements in group 2A will have 2 valence electrons. Group 3A will have 3 valence electrons, and so on and so forth. So let's look at a few examples of Lewis symbols. So for sodium, the symbol for sodium is Na, and sodium is in group 1A in the periodic table, and so it will have 1 valence electron. And so as you can see here, there's a dot right next to the symbol of the element. That's basically the valence electron represented by a single dot. And then group 2 elements, such as calcium, will have 2 valence electrons. And so you draw the symbol of the element, which is Ca for calcium, and then you draw 2 dots around it, as shown here. So this is the Lewis symbol for calcium. And then we can do the same thing for other elements. For example, in group 3, we have boron, which has 3 valence electrons, 3 dots. Carbon has 4 valence electrons, so it has 4 dots. Nitrogen has 5 valence electrons, so 5 dots. 6 dots for oxygen, 7 for fluorine, and 8 for neon, which is one of the noble gases in group 8, group 8A in the periodic table. So just by knowing the number of valence electrons of a given element, we can predict and determine a lot of that element's physical and chemical properties. One example is reactivity. Group 1A elements, for example, the alkali metals, are known to be the most reactive elements in the periodic table. And the reason behind that is because they only have 1 single valence electron. The group 2A elements, known as the alkali earth metals, are also known to be reactive, but relatively less reactive compared to the alkali metals. And group 8A elements, the noble gases, are known to be the most stable elements in the periodic table. And the reason behind that is because they have a full S&P sublevels. They have a full octet, so to speak. So they have 8 valence electrons in their outermost shell. All of the noble gases in group 8 have a complete octet, meaning 8 valence electrons. Like, for example, we have neon, argon, krypton, and xenon. These noble gases are considered stable, and the reason why is because they have a complete octet, or 8 valence electrons. So why is it that helium, also a noble gas, is considered stable, just as stable as the other noble gases? Well, let's take a look. So helium, the first noble gas, is just as stable as the rest of the noble gases, even though it only has 2 valence electrons. They call it a duet, right? 2 valence electrons. And the reason why is because if you look at the first energy level, right, using the quantum mechanical model of the atom, n equals 1, you can only have 1 orbital in that first energy level. And that orbital is the s orbital. And so the maximum number of electrons that an s orbital can hold is 2. And so the 1s orbital is already maxed out for helium. It's 1s2. So the outermost shell for helium is already completely filled. And that's what makes helium stable, just as stable as the other noble gases. So here's a schematic illustration that basically shows you that the first energy level for helium is already maxed out with 2 electrons. And so this is the outermost shell for helium, and it's already completely filled, which makes it stable. So here's a few important points that you should remember before we move on to the next concept. So reactive metals are considered unstable because of the fact that they have less than 8 valence electrons. So they have an incomplete octet, whereas elements that are unreactive are considered stable because they have a complete octet or 8 valence electrons. Those elements that are unstable will form bonds with other unstable elements in order to complete its octet and achieve stability, just like the noble gases. And when these elements form a bond, they either share or transfer electrons to get the full octet. In other words, these elements become isoelectronic with the noble gases, meaning they have the same number of electrons, number of valence electrons as the noble gases, as well as the same electron configuration as the noble gases. So again, we will focus on two types of chemical bonds here. The first one is ionic bond, which is basically the transfer of electrons between two elements. And the second one is covalent bonding, which is the sharing of electrons. And as you'll see later in this chapter, the atoms involved in bonding for both types of chemical bonds will obtain a complete octet, or a stable electron configuration similar to those of the noble gases. And this is known as the Octet Rule, the rule of 8 valence electrons. So first, let's take a look at ionic bonding, which is the bonding present in all ionic compounds. And ionic bonding, again, is the transfer of electrons from the metal to the non-metal. An example here is for potassium chloride. So an electron is transferred from the metal potassium to the non-metal chlorine. So how is this electron transferred from the metal to the non-metal? Let's take a look. So when you draw the Lewis symbol for each atom, we have potassium here on the left, which has one single dot, which is the valence electron for potassium, and chlorine, which has 7 valence electrons. So as you can see here, chlorine only has 7 valence electrons. And in order for this to become stable, it has to have a total of 8 valence electrons. And how does chlorine get another valence electron? Well, from the metal potassium. And so this potassium will transfer its valence electron to the chlorine, satisfying the octet rule. So now we have a chloride ion, which has a full octet, and the potassium also now has a full octet because its outermost shell is now complete. So now both of these ions, the chloride and the potassium ions, are isoelectronic with the noble gas argon. So that means that they have the same number of valence electrons, the same number of total electrons, and the same electron configuration. And that basically makes these ions stable because they are now isoelectronic with the noble gas. So let's take a look at the electron configuration for potassium atom. Okay, a neutral potassium. As you can see here, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, for a total of 19 electrons. What about for potassium ion? So the potassium ion, you remove 1 electron from the outermost shell. And so that means we're taking 1 out from the 4s. And now the potassium ion has this electron configuration shown here. So 1s2, 2s2, 2p6, 3s2, 3p6, which is isoelectronic with the noble gas argon, meaning same electron configuration as argon. So as you can see here, this potassium ion has now a complete octet. The outermost shell, right, the highest S and P sublevels are completely filled. So you have 3s2 and 3p6. And same goes for the chloride ion. So if you write out the electron configuration for the chlorine atom, it looks something like this. So as you can see, the highest S and P sublevels are incomplete. So we have a 3s2 and a 3p5. And by adding a single electron to the 3p sublevel, it becomes completely filled. So now we have a chloride ion here with 8 valence electrons. So the next concept that I want to talk about here regarding ionic compounds is lattice energy. So ionic compounds have lattice energy because all ionic compounds have what they call crystalline lattice, which is basically a specific arrangement of ions within a given ionic compound. So what is this lattice energy? Lattice energy is basically the energy associated with the formation of a crystalline lattice of alternating cations and anions from gaseous ions. So lattice energy is related to this concept known as melting point. And melting point is basically the temperature at which a solid melts. So if you have two ionic compounds, you'll be able to predict which one has a higher melting point based on their relative lattice energies. So there is a trend in lattice energy. So make sure that you remember this equation shown here. So this is lattice energy, and it's proportional to Q1 times Q2 divided by R. And Q here is basically the charge on the ion. So if you have two ions, that would be charge on ion 1 and charge on ion 2 divided by R, and that's the distance between the two ions. So according to this equation shown here for lattice energy is dependent upon two things: ionic charge and the distance between the ions. And this distance R between the ions is basically dependent on ionic radius, right? The size of the ion. So as R increases, as the distance between the ions increases, lattice energy decreases. So that tells us that lattice energy is inversely proportional to the distance R. So let's take a look at a few examples here. So we have a bunch of ionic compounds shown here that contain chloride ions. So the only thing that's variable here is the size of the cations, right? So you have lithium chloride, sodium chloride, potassium chloride, cesium chloride. So in terms of the ionic radius, the trend in ionic radius, size increases as you move from right to left and from top to bottom in the periodic table. So looking at lithium, sodium, potassium, and cesium, these are elements in group 1. So lithium is up top, and you move down the column to sodium, potassium, then cesium. So according to the periodic trend regarding ionic radius, cesium is the largest in this example, right? And lithium would be the smallest. So as the distance increases, lattice energy decreases. And so that means that as the cation size or ionic radius increases, the lattice energy decreases. And that's basically what's observed here in terms of their lattice energy. So you can see that the lattice energy of lithium chloride is negative 834 kilojoules per mole. The lattice energy for cesium chloride is negative 657 kilojoules per mole. So in terms of magnitude, lithium chloride has a larger lattice energy compared to cesium chloride's lattice energy. So this illustration right here shows you the distance between the two ions. So for example, lithium chloride, the distance between the two ions is 245 picometers, whereas for cesium chloride, it's 348 picometers. And so again, as the distance increases, the lattice energy decreases. And in terms of ionic charge, lattice energy is directly proportional to the ionic charge. So as the ionic charge increases, lattice energy also increases. So an example here is between calcium oxide and sodium fluoride, right? So the ionic charge of calcium is positive 2. The ionic charge for oxygen is negative 2. So when you multiply the 2, you get a magnitude of 4. 2 times 2 is 4. Whereas for sodium fluoride, you have a positive 1 and a negative 1 for fluoride. So that's a magnitude of 1. And so because of that, calcium oxide has a larger lattice energy than sodium fluoride. You might want to take note that the ionic charge, like Q1 and Q2, actually has a larger effect on lattice energy in terms of magnitude compared to the distance between the two ions. So let's take a look at this example again. Calcium oxide versus sodium fluoride. So here's the equation again. But we're going to ignore R, the distance between the two ions, because R has actually little effect on lattice energy. So we're going to focus on Q1 and Q2, which are the ionic charges. So calcium oxide. Calcium has a positive 2 charge, oxygen has a negative 2 charge, sodium has plus 1, and fluoride has minus 1. And so looking at Q1 and Q2 only, we can predict their relative lattice energies. So for calcium oxide, the magnitude is roughly 4. For sodium fluoride, the magnitude is only 1. And so based on the charges, the ionic charges, calcium oxide has a larger lattice energy than the sodium fluoride. Alright, so let's look at a few examples here. Arrange the following ionic compounds in order of increasing magnitude of lattice energy. So we have calcium oxide, potassium bromide, potassium chloride, and strontium oxide. So the first thing that you should do here is to determine the ionic charges, because Q1 times Q2 have a larger effect on lattice energy. And then so now multiply Q1 and Q2 for every single ionic compounds, and you get these values shown here. So as you can see, strontium oxide and calcium oxide have larger lattice energy in comparison with KBr and KCl. And so now the question is, which one has a larger lattice energy, calcium oxide or strontium oxide? Well, now we have to take into account the distance between the two ions, right? The value of R. And how do we do that? Well, we have to look at the ionic radius. So when you compare the ionic radius of calcium and strontium, strontium is actually larger. And so that makes the distance between strontium and oxygen larger compared to the distance between calcium and oxygen. And so because of that, strontium oxide has a lower lattice energy than calcium oxide. Okay, so now we know that calcium oxide has the largest lattice energy, followed by strontium oxide. What about KBr and KCl? Well, we know that they have the same Q1 and Q2 values, so the only thing that we need to take into account would be also the value of R. And so, which one has a larger ionic radius? Bromide ion or the chloride ion? Well, bromide ion is right below the chloride ion in the periodic table. And so that would have a larger ionic radius. So in that case, KBr has the lowest lattice energy. So in that case, we have calcium oxide followed by strontium oxide, and then KCl, and then KBr would have the lowest lattice energy. And this is how you would arrange it in terms of increasing magnitude of lattice energy. KBr is less than KCl, KCl is less than strontium oxide, and strontium oxide is less than calcium oxide. And as I mentioned in the beginning, lattice energy is related to melting point, which is basically the temperature in which a crystalline solid melts. And the higher the lattice energy, the higher the melting point. So if we were comparing KBr with calcium oxide would have the largest melting point, and KBr would have the lowest melting point. So from this point going forward, we're going to focus on covalent bonding, which is basically the sharing of electrons between atoms. And you're going to learn the simplest bonding theory here, which is the Lewis theory, and it utilizes Lewis dot structures. And we're going to use Lewis dot structures to show how atoms are bonded together using Lewis symbols. So how do we draw Lewis dot structures? Well, let's focus on simple molecules like diatomic molecules involving only two elements. So for example, fluorine gas. So a lot of diatomic gases like fluorine gas, chlorine gas, nitrogen gas can easily be drawn using Lewis dot structures. So the first step here is to basically draw the Lewis symbols for each atom in that chemical formula. And then we're going to apply the Octet Rule in order to make sure that each atom in that chemical formula contains 8 valence electrons. So here's the first step. So we draw the Lewis dot symbols for each atom. So you have fluorine atom here on the left, the second atom on the right. And you can see that there's a total of 7 valence electrons, or 7 dots, surrounding fluorine. And so because they lack one single electron, these 2 electrons here will basically be shared between the 2 atoms. Okay, so each fluorine atom lacks 1 electron to satisfy the octet rule. In order to attain a full octet, they must share those electrons. And so this fluorine right here will share its single electron with this fluorine, and the second fluorine will also share its unpaired electron here with the other fluorine atom. And so it looks something like this. So now these 2 electrons right here are being shared by the 2 fluorine atoms. And so when you count the total number of valence electrons, this fluorine right here has 2, 4, 6, 8 valence electrons, and this second fluorine right here also has 8 valence electrons. So this is the Lewis dot structure for the fluorine gas molecule. And these two electrons right here that are being shared by the two fluorine atoms are the bonding electrons, because those are the electrons that are involved in bonding. And we call this a bonding pair. And all the other electrons that are not involved in the bonding are called non-bonding electrons, or lone pair. So you have a total of 2, 4, 6, 8, 10, 12 non-bonding electrons, or a total of 6 non-bonding pairs, or 6 lone pairs. And we only have one bonding pair, or 2 bonding electrons. And this pair of bonding electrons can be represented by a line, as shown here. So this right here is a bond, a single bond between the two fluorine atoms. So let's look at another example here. Draw the Lewis structure for oxygen gas. So again, oxygen gas is a molecule. It's a diatomic molecule. So the first thing that you want to do here is to draw the Lewis symbols for each oxygen atom. And then again, apply the octet rule to make sure that each atom has a complete octet, 8 valence electrons. So here are the Lewis symbols for the oxygen atom. So you have oxygen on the left and the second oxygen on the right. And you can see that each oxygen lacks 2 electrons because they only have 6 electrons. And so that means that all these 4 electrons here will be shared equally by the 2 oxygen atoms. And so you can combine them as shown here. And so if you count the total number of electrons for each oxygen atom, you can see that this oxygen right here, for example, has 2, 4, 6, 8 electrons. And this oxygen right here also has now a total of 8 valence electrons, 2, 4, 6, and 8. And you can simplify this using 2 lines, right? So each line contains a pair of bonding electrons. And we call this a double bond. A double bond contains 2 bonding pairs, or a total of 4 bonding electrons. And here's the third example. Draw the Lewis structure for nitrogen gas. So again, nitrogen gas is also a diatomic molecule. Again, the first step here is to draw the Lewis symbol for each nitrogen atom and then apply the octet rule. So here's the Lewis symbol for the nitrogen atoms. You can see that each nitrogen has 5 valence electrons and they need 3 electrons each in order to have a complete octet, 8 valence electrons. And so that means that both nitrogen atoms will need a total of 6 electrons shared, right? So that means that all these electrons right here, 1, 2, 3, 4, 5, 6, will be shared by both nitrogen atoms. And so all you have to do is draw a line connecting the 3 dots, or a total of 6 dots. And then you can clean it up a little bit. So you have a total of 2, 4, 6 electrons that are shared. And those are going to be the bonding pairs. So you have a total of 3 bonding pairs and one pair, second pair, 2 pairs of non-bonding electrons. We can also draw the Lewis dot symbol or the Lewis dot structure for nitrogen gas as shown here, where you have a total of 3 lines, and this is known as a triple bond. So a triple bond contains 3 bonding pairs, or a total of 6 bonding electrons. So hydrogen gas is also a diatomic molecule. Okay, so you have H2, which is hydrogen gas, And hydrogen, the element hydrogen, is a special case because it doesn't have to follow the octet rule because it only has one single electron. So once a hydrogen becomes isoelectronic with helium, then it will become stable because it's isoelectronic with the noble gas, meaning the first shell or the first principal energy level will now be completely filled with 2 electrons. And so hydrogen only needs one single bond and it will be stable, as stable as a helium atom. So let's take a look at hydrogen gas. What would be the Lewis dot structure for hydrogen gas? So again, we'll follow the same steps. We'll draw the Lewis symbol for each hydrogen atom and then go from there. So here's hydrogen gas. The Lewis symbol for hydrogen, single dot, 1 valence electron, and then both electrons will be shared equally by the hydrogen atoms. And what you have is basically a single bond. So you have a single bond between the 2 hydrogen atoms, and they are stable because again they become isoelectronic with the noble gas helium. So before we start looking at slightly larger molecules and drawing their Lewis dot structures, let's look at electronegativity and bond polarity. When looking at Lewis dot structures of molecules, electrons may seem to be shared equally by the atoms. So for the molecules that we looked at earlier, the homonuclear diatomic molecules like hydrogen gas, fluorine gas, nitrogen and oxygen gas, the bonding electrons are shared equally. But in a lot of other molecules that are heteronuclear diatomics, for example, and other larger molecules, the bonding electrons are actually shared unequally between atoms. And the reason behind that is because some elements are more electronegative than others. So what that means is that some elements in the periodic table have the ability to attract electrons more towards themselves than those that are less electronegative, meaning more electropositive. So here we have hydrogen fluoride as an example, and hydrogen fluoride is a heteronuclear diatomic molecule, meaning it's a molecule containing 2 different atoms. So we have hydrogen and fluorine. And this is basically the Lewis dot structure for hydrogen fluoride. You can see that fluorine has a total of 8 valence electrons, so it's isoelectronic with a noble gas. And this hydrogen right here has 2 electrons, which makes it isoelectronic with helium. And so you have 1 pair of electrons right here that's being shared by the 2 atoms. Now, one may think that this pair of electrons are being shared equally by the 2 atoms, when in fact they're not. They're not equally shared by the 2 atoms. And the reason why is because fluorine is more electronegative than hydrogen. And so fluorine is actually attracting those electrons more towards itself than the hydrogen. So that makes fluorine the more electronegative atom and the hydrogen the more electropositive atom. And because of this difference in their electronegativity, it creates what they call a separation of charge, where you have a partial positive and a partial negative charge. Because technically, these are not ionic, these are not ions, right? This is not an ionic compound. And so they can't have a full charge. So they call them partial positive and a partial negative. So the fluorine in this case will receive that partial negative, and the hydrogen will receive the partial positive because it's more electropositive, whereas the fluorine is the more electronegative atom. So let me say that again. The more electronegative atom receives the partial negative symbol, and the less electronegative atom will receive the partial positive symbol. This is basically delta with a negative charge for electronegativity or partial negative charge, and delta positive for electropositive or less electronegative atom. So this charge separation between two atoms is represented by a vector, an arrow pointing towards the more electronegative atom and the positive end towards the more electropositive atom. So when we're looking at hydrogen fluoride again, the arrow would be pointing towards the more electronegative fluorine. So fluorine here is more electronegative, and so the head of the arrow would be pointing towards fluorine, and then the positive tail would be pointing towards hydrogen, which is the less electronegative atom. So here's a few more examples. We have hydrogen chloride, hydrogen bromide, and hydrogen iodide. So chlorine is more electronegative than hydrogen. Bromine and iodine are also more electronegative than hydrogen, and so the vector, the polar vector, as they call them, will be pointing towards the more electronegative element. So when you put a hydrogen fluoride gas inside a chamber containing a negative and positive plates, hydrogen fluoride will actually orient itself so that the more electronegative fluorine will be facing the positive plate, and the less electronegative hydrogen will be facing the negative plate. And this experiment here basically validates the theory that electrons surround the more electronegative atom, which also supports the idea of unequal sharing of electrons between atoms. And it was actually Linus Pauling who received the Nobel Prize regarding this work, who determined and quantified the electronegativity for each element in the periodic table. So electronegativity is another one of those periodic trends. So the trend here is that fluorine is the most electronegative atom. So it increases, so electronegativity increases from left to right towards fluorine and from bottom to top towards fluorine. And so the more electronegative elements will receive the partial negative charge, and the less electronegative element will receive the partial positive charge, and then the vector, the arrow, will be pointing towards the more electronegative element. And this arrow right here is known as the polar vector. Okay? And this separation of charge makes the bond polar. So the bond between the hydrogen and fluorine is polar. So that's the definition of polarity. So when the bond is between two different elements with different electronegativities, then that bond that's formed between them is known to be polar. But if the electronegativity between the two atoms are similar, like for example in carbon to hydrogen bond, then that bond is considered nonpolar. So again, this bond between hydrogen and fluorine is known as polar covalent bond. And the greater the difference in electronegativity between the two atoms, the more polar the bond. So let's look at an example here. So which one do you think is, or which molecule do you think has the most polar bond? So we have three different molecules here. We have hydrogen fluoride, hydrogen chloride, and hydrogen bromide. So in the periodic table, fluorine is the most electronegative element. Okay, so this is the most electronegative element in the periodic table. And between chlorine and bromine, chlorine would be more electronegative than bromine because chlorine is just right below fluorine, and right below chlorine is bromine. And electronegativity increases from bottom to top towards fluorine. So in that case, this bond between hydrogen and fluorine is the most polar bond among these three molecules, followed by hydrogen chloride, and then hydrogen bromide would have the least polar bond. So if you have two identical atoms that are bonded together, then you have a nonpolar bond. Okay? So all the homonuclear diatomic molecules like hydrogen gas, chlorine gas, bromine, nitrogen, oxygen, fluorine gas, they all contain a nonpolar bond because there's no difference in their electronegativities. And so if there's no difference in electronegativity, you have no separation of charge. In other words, the bonding electrons are shared equally between the two atoms. So all of these homonuclear diatomics will form a nonpolar bond regardless whether it is a single, double, or triple bond. because there's no difference in their electronegativity, there's no separation of charge. So here's a few more examples. So we have two different molecules here. So between carbon and chlorine, this bond right here is considered polar because chlorine is more electronegative than carbon. Same thing with this bond right here and this bond right here. So all these three single bonds here are considered polar because chlorine is more electronegative than carbon. Same thing over here. The double bond between carbon and oxygen is considered a polar bond. And again, this carbon to chlorine bond is also a polar bond. But the bond between these two carbon atoms is considered nonpolar because there's no difference in their electronegativity. For this molecule right here, the carbon to fluorine bond is considered a polar bond, and because the difference in electronegativity between carbon and hydrogen is minute, then the bond is considered nonpolar. So the strength of a polar bond can be quantified using what they call dipole moment. And dipole moment has this symbol, which is basically the microsign or microsymbol. So if the dipole moment is close to zero, then that bond is considered a nonpolar bond. But if the dipole moment is non-zero, then it's considered a polar bond. The greater the difference in electronegativity between the two atoms, the greater the dipole moment. In other words, the greater the dipole moment, the more polar the bond.